In this video, we will review Avogadro's law and the ideal gas law. So you may remember Avogadro. Avogadro's number is 6.02 times 10 to the 23rd, and that's describing how many particles, or number of things, are in 1 mole of something. So he found this number basically by analyzing different gas molecules. He found that a given volume of gas had the same number of particles, and if we measure 1 mole of those particles, it has 6.02 times 10 to the 23rd number of particles. So his law actually relates the number of particles to volume. So remember, he hypothesized that equal volumes of gas, no matter what the gas is at the same temperature and pressure, contain the same number of molecules. He knew that volume would be directly proportional to the number of moles of gas molecules in a sample. So they might not weigh the same, but he knew that they had the same number of particles or molecules in that sample. So if volume of a gas is directly proportional to the number of moles of gas, which he represents as N, when T and P are held constant, then we can show that relationship as V over N, volume over number of moles, equal to this constant. So if one increases, the other increases. If one decreases, the other decreases. And we can also compare one sample under different conditions to solve what the new volume or new number of moles would be. If we use a rigid container where V is constant, then P is able to replace V in the equation. So if we increase the number of moles of a substance, we would expect the pressure to increase, which makes sense because what is pressure? It's the amount of force that those particles are exerting on the sides of their container. Okay, so here we have another example. We have a balloon with 1.9 liters and 0.092 moles of helium gas. If we have 0.021 moles of additional helium added to that balloon, while the temperature and pressure are constant, what's the new volume of the balloon? So this is the relationship we are using. Pressure and temperature are both constant. Our volume and number of moles are changing. Our initial volume is 1.9 liters. Initial moles is 0.092 moles. And our second number of moles, you have to be careful the way you read this, we're adding 0.021 moles. So we have to add those two together, so our final N2 number of moles is 0.1130 moles. And we are solving for V2. So once again, we can rearrange this equation so that we can solve for V2. And we get V1 times N2, second number of moles, divided by N1 equals V2. For units, moles are moles. That unit is the same, and our volume is going to end up being liters because our initial volume is in liters. So I'm going to take our original volume, 1.9, multiply by your second total number of moles, 0.1130, divide by the initial number of moles, 0.092, and we find that the new volume, V2, is 2.33 liters. And once again, we can think, does this answer make sense? Our number of moles increased, so we would expect that our liters volume would increase, and it does, so this answer does make sense. So I'm pretty confident that is correct. Okay? Next, we're talking about the ideal gas law, and this is what you might have called PIVNERT. That's usually what I refer to it as, because that's just how you would say the ideal gas law if it was a word. So PV, that's pressure volume, N is number of moles, R is a new constant we'll talk about, and T is temperature. So the ideal gas law truly combines everything. It's not just the combined gas law, because the combined gas law was under the circumstance that you had the same number of moles, a constant N. This, your number of moles, N, could also change. So that's how the ideal gas law is different than the combined gas law. And it is under the assumption that when we use this equation, it's an ideal gas, even though there are no such thing as ideal gas. But we use this for real gases all the time because even though they're not perfect, they are pretty close to ideal, Even though they are not perfect, we kind of make the assumption when we use PivNert. And we get pretty close answers, so it's been working so far. So PivNert, like the combined gas law, it's used when nothing is constant. So temperature is not constant, pressure is not constant, and volume isn't constant. Or they're not a constant variable. Unlike the combined gas law, this ideal gas law can be used for samples with varying numbers of moles, like I said before. So remember, PV over T equals K, that's our combined gas law. Here we are also considering N. N goes on the bottom with T because it is directly related to pressure and directly related to volume, just like temperature is. And instead of K, we use R. R is the ideal gas constant, so it's a special constant, so we don't just represent it with K, we gave it this value R. So any value for pressure, volume, number of moles, or temperature can be found given the ideal gas law and enough information. The value for R does vary based on your units for pressure, temperature, and volume. So your temperature unit should always be Kelvin, as we've talked about before, and typically your volume for your unit for volume is going to be liters, most often than not. So here, with this constant, you would have to make sure that your volume is in liters. If your volume is given in milliliters, just do a simple 3 decimal switch to go to liters. Pressure is the one that varies the most of these 3 variables because there are a lot of SI units, basically units that are acceptable in science, for pressure. It could be kilopascals, it could be millimeters mercury, or it could be atmospheres. So there's 3 options there for pressure, which is why we have varying values for R. You don't need to memorize these values of R. Any value of R that you would need on the AP exam would be given in a packet that you get. So there's no need to memorize it. Just be aware of which value you are using based on your unit for pressure, and make sure that your volume unit also matches for the value of R. So if you're given pressure in kilopascals, it would be equal to 8.314 liters kilopascals per mole Kelvin. If you're given atmospheres, which is the most common, which is why I highlighted it, your value would be 0.0821 liters times atmospheres per mole Kelvin. And if you're given millimeters of mercury, which I would say is the least common, it would be equal to 62.36 liters times millimeters of mercury per mole Kelvin. Okay, so once again, you do not need to memorize these. They are given to you on the AP exam and any test that you will take in my class. So next we're going to do a problem using the ideal gas law. So we want to know what volume is occupied by 3.760 grams of oxygen gas at a pressure of 88.4 kilopascals and a temperature of 19 Celsius. Assume oxygen is an ideal gas, okay? So notice they didn't give us moles of oxygen, they gave us grams. Does that mean we can't solve this problem because PivNert doesn't have grams, it has moles? Absolutely not, because we can easily convert from grams to moles using molar mass, okay? So the molar mass of oxygen gas, remember oxygen gas is not oxygen, just oxygen, it's O2. So oxygen is one of the diatomic elements. So you have 2 atoms of oxygen. So the molar mass of oxygen gas is equal to 32 grams per mole, which I have laid out right here. I have 1 mole over 32 grams. That's saying there's 1 mole in 32 grams. Same thing as saying there's 32 grams in 1 mole. It's just different ways of saying things. So since I'm given grams, I want to multiply by moles and divide by grams so that unit cancels out, and I am ultimately finding the moles of oxygen gas. Okay, so I find that that is equal to 0.1175 moles of O2 gas. So just because they didn't give me moles doesn't mean that I was stopped from using this equation and ultimately solving the problem. So what are we solving for? Volume. Okay, so here I can rearrange PivNert to solve for volume. So that would be V equals, I just have to divide both sides by P, and RT over P. Okay, and then it's a simple matter of plug and chug. you'll notice that the R I'm using is 8.314 because my pressure was given in kilopascals. Everything else is in a unit that works for that R value. And based on the value for R, my unit for volume is going to be liters, okay? So now I'm good to plug and chug. So I take my number of moles, 0.1175, times my R value, 8.314, times the temperature, which should be in Kelvin, 292. And then I divide that by the pressure, which is 88.4 kilopascals, and I get a volume of 3.23 liters, and that is my final answer. Okay, so you could use this to solve for pressure, volume, temperature, or number of moles. You will be using ideal gas law a lot, even if it's like one step in a problem. A lot of times we'll use it to solve for number of moles and then use that number of moles to solve for something else. So this is a mathematical equation you will be using a lot. So keep PivNert on your brain and let me know if you have any questions.